Chapter 2, Computer System. Lecture 1, Processor. Okay, we are on Chapter 2 of the Computer System Organization. Digital computer consists of interconnected system of processor, memory, I/O devices. So this chapter basically is on the system architecture. That actually the chart I talked about before. You have the processor, you have the memory, you have the I/O, and then these three connected by the 3 bus. What are the 3 bus? Still remember?
There's the control one.
Control.
The data.
Data.
One more.
One more. To find data. Use what?
Find data. Address. Oh.
Okay. So remember this one is the read-write control. Right? This one is the bits. Right? This one is address. Okay. Okay, remember that when actually sometimes people write in the chart with the cut and then 32, that means the bus width is 32 bits, so it's like 32 wire together. Okay, and sometimes they use the array notation. Okay, that means that how many bits they are. Okay, so that's what we are talking about right here. Okay, so this whole computer system organization course has 2 main topics. One is called assembly, right? One is this one called computer system organization. So the primary study is this. So we try to understand what's inside here, right? And we understand that in order to learn system programming, so we need a language, and that language is this one called assembly. Okay, is this one called assembly, and assembly need to program on something here, right? That's the job you're trying to do. Try to process the CPU, process this, something like that. That's the system program we try to do. So we need to know about this computer system organization. Same thing, we need to know this. And computer system organization, we need to go back to the basically study in the previous chapters 6 level chart. In the previous chapters 6 level chart. It basically is actually talking about is level 0 to level 5. And computer system organization mainly focus more on up to here, maybe 3 a little bit, but mainly 1 to 0. Okay, the 3 level to be studied are over here. Okay, then I don't know whether you install or not, but last time you probably installed this Qt sim, right? This one called Qt spin. Okay, I'm sorry, Qt spin. So after you install this Qt spin, actually here are some programs you can actually load. You can actually load a like hello world.s is a assembly code. That one actually, if you look at it, is under the Qt spin. There's a hello.
Yeah, I have to download this program later.
Yeah, and this one actually, if you open that one, that's under this one. There's a Qt spin. Under the Qt spin. Over here, there's a hello world.s, and you can actually open it by this one called Notepad++. The real program is only just this part. Okay, other thing with punch, they are all commands, so it's actually not important. The real code just this part. Okay, and the purpose of this is to print out the so-called hello world. Okay, so this one actually, as you can see right here. It has .data. This one means data section. This one .text. It means the code section. Okay. So
what's the data section? What does that mean?
It's same as the C language. Remember the C language? C language, I say, is a data section. When you have a global variable, you put it here.
Oh.
So basically, you put a hello world in ASCII format. So it's just, this one is just like CHAR A star equals hello world. So this line actually just like that. You know what I'm saying? This line just like that. Okay, and it says message location, memory address location. So MSG is a label. It's actually a address argument string. Okay, so that actually put that data being put into the memory location is called data section. Right, and there is an instruction section, and in the instruction section, I declare something called main. Main is a main pointer. So this one is a starting address for the call. After that, I put like load 4 to what to this VO, that's a register, and then I actually load the argument and call print out function, and it will just print out this message for you. So actually, this is a print out, only a print out. So there is a system call. You call certain service routine by the system. So system call is something like a function, but it actually is an IO function called system call. And sometimes you use a system call to finish the program. So system call exit, that will actually finish the program. So we are not going to go over this assembly yet, but that's telling you that's the subject that you are going to study. Two things: you learn your program, assembly program. The other one you learn, we try to understand how computer is set up and how it will work. Okay, these are the two purposes for this course. Okay, so now we are on the chapter 2, and then that one, that's single program. If we actually here we actually open this recent program. This one called Hello World, and then if you do click run, see here your console print out Hello World. So this one Qt spin is somewhat like Dev C++, you know, for assembly, something like that. But it's just a runner. You can step over. There's a step over. There's just like a little bit like debugger. And then the scoreboard right here on the left-hand side is a register scoreboard. So it shows you the register status right now.
What does that mean?
So you have your own CPU, right? You have your own CPU, right? And inside your CPU, let me open the file. Inside your CPU, you have this, right? You have this one, computer organization. Okay. So basically, you have different register. And when I actually run my Hello World program, my register keep changing, right? And those changing register value are shown on the left-hand side. These are the register 1, 2, 3, 4, 5, something like that. It's shown on here. PC is called program counter. Okay. And about what this means, actually, today we are going to cover this one, chapter 2, to talk about it. Okay. But basically, that one is actually keep track of the information over here. So you run the program step by step. Say here you have this one called run and continue, right? Here you have the initialize simulator. So I can hit this one, initialize the simulator. So the program go back to the starting point. Then I can actually pause, or I can just actually run. Run means run the whole program. So here I can use this one called single step. Single step means that in my code segment, I kind of step by step. After my first step, my program is right here, right? And it show up the result there, and then I hit it equal to the next stage. Hit it equal to the next one, and then this program counter is changing. So right here, program counter go to 40000C, and then that's the program counter. Okay, program counter means that current instruction is where, and then I keep hitting this one. You go to the next step. You go to 40000110. Okay, and then the register result like this. Okay, so keep going, keep going, keep going, something like that. Okay, until you want to finish, it just go wrong. Okay. So that actually is just like running the. You are actually simulating like you have a CPU like that, and then you try to load something here, and then go back, something like that. So here the scoreboard, this one we call it scoreboard, like baseball scoreboard. You keep track of whatever is going on in your computer. Okay, so that's the register, and the program actually mimic the operation of the computer. So today we are going to talk about what is a computer architecture. Basically, this is very basic computer architecture. And then starting from next chapter, we'll talk about the basic logic and start to go into the programming for using the assembly. Is that okay?
Yes.
Okay, and today we are going to do this one, computer system organization. So let's look at the processor. So now we are talking about processor and those two parts, we call it the memory and I/O part. Okay, so now I terminate the program. We are not going to touch it too much today. Okay, so let me actually bring up this. Okay, so basically your computer, you have a central processing unit. People call it central processing unit, so it call it CPU, but usually some people call the processor CPU as well. But this name sometimes is the whole computer. Some people also call it CPU, but that's the new name. The real CPU is the central processing unit. That means the control unit, ALU, and register. So that actually means that the chart we see here, that's a data bus. Okay? And then we have a memory, we have the disk, we have the printer. These are I/O devices, and they are connected by the 3 bus. Okay? The next one, we have the basic data bus. And you have the control unit just beside it, and you actually doing control on it, and you get an instruction from memory, and then use that instruction to do decode, and then control whatever operation on the data bus. This side is data bus. Data bus including register plus your ALU. Okay, and this is the most simple one as a processor. And here it said that the Maneuver machine. Maneuver machine actually means the C double plus. Okay, and Maneuver introduced memory to computer. So it's a memory-based computer is called Maneuver. And nowadays, every processor are C machine, C double plus machine. They all build upon C double plus requirement. Not Python, not Java. All CPU are built upon basically the first language they port is C double plus. That's why C double plus is so important in computer programming and computer organization. So again, one thing I would like to emphasize many times so far, the C memory model. C memory model is pretty important. Okay. And this one, basically, when you run a program, you have a few things you need to know. That is your code frame, your stack and queue. This one are called stored in the stack segment, right? Global data area. This one is your data segment. So when you have the hello world, it actually stored into this region. But it's not something like the size actually state segment, data segment, and code segment, they are of equal size. Not like this one, okay? This one overemphasize the stack part, okay? And then the code segment, you put your program in the code segment. Okay, so you basically have the code segment, data segment, and the stack segment. Okay? So your memory, you basically put your program call, functional variable, argument variable, local variable, return value, and global variable, you store your dynamic allocated, variables. So that's what we call memory model. Okay? That's what we call memory model. And again, because I say that all machine we know so far is called Maneuver machine. Maneuver machine is a memory-based machine. And actually it has the memory model. So whatever you learn so far for the memory model is just like what we see over there. Even the CPU's memory model is the same as the C language memory model. And C language is the lowest level, high level language for normal processor. So here we have a central processing unit. We had a bus with the I/O unit. Okay. So that's that. And the first thing I need to tell you is a program. Okay. A program is just like the real program that actually run by. I need to bring up that again. Bring up the Qt sim again. Okay. Qt spin. Okay. Okay. This one calls Qt spin. Okay. So your program actually has data and text, right? If I click data, you have the data like this stored in your memory, right? That's your microprocessor. Okay, that's the memory. Your memory kernel data, they call kernel data segment, and there is something called user stack. The difference between kernel stack and user stack is that kernel stack is used for operation system and system call. So if I do printing, actually I'm transferring my control from my code in my own program. And if I actually doing let me actually bring out the program again. Qt sim. Let me bring out this hello world again. So this one actually is stored in the data section, right? Text I'm storing in instruction segment, data stored in data segment, right? So this one you have the data stored in there, but this one actually is what? It's your users data segment. But there is another one called kernel. Stack the same thing you have. So when you actually do system call, you jump into a system call maybe similar to print, and then you do function there, and then you jump into here. So there is a system kernel mode program need to handle. That's the so-called kernel mode. So there is a kernel mode stack. That's the system program. You may call the printing function for that. And then you may have this one called stack segment, your own. And there is also a user data segment. User data segment is actually the one we put hello world in. Stack is for our functional code. So here, as you can see, it show you the different data element. But because right here we do not specify too much data, okay, so it's something like this. And the program sector is called, you have the programming sector, so this is instruction segment and then kernel text segment. So here, actually what it is I have a memory model, right? And then my instruction section is described as right here. So it's starting from 40000 something, okay? That's my instruction segment. And then I have data segment. And here you say my data segment, you put a 1000 something. So that is a data segment. And here I also have a stack segment. So my stack segment right now is actually stored at 7FFFF something. So this one actually is like A0000 something. It's just a few bit some distance away from there. Okay. So these are the three segments I have for my user mode program. Okay. So your program put in here, your data put in here, your stack put in there. They have separate edges and you show it there, right? That we call it the memory model. For C language, the same thing. The optimal, the final compile code will be there. And my real program only just this much, okay? My hello world program only just this much. And then you run, you basically every time you pick from the address 40000 here. So what happens is like when you run the program, you have a CPU processor, let me call it processor, and you have a memory, right? In the memory is lined up like your code segment, data segment, and your stack segment over there, right? So actually I started from my starting point of the code segment. I do this. load something to some register. So you will load something to some register. But before that, actually, I need to get the instruction, get the program instruction, and put into my instruction buffer. And then each time I see this instruction, so I run it and use my decoder or my instruction decoder for control unit, and then control my data path to load data to some register. So basically, this is a program. This is an assembly program, and then I actually run this instruction, and this instruction actually being loaded from my memory to my CPU, right? And then I decode it, and then after I decode it, actually I load the data from some certain address to one of my register. Okay, so that's what is going to be done. So every time I have a program counter called PC, sometimes you call PC.
Wait, can you repeat it again? So you go from instruction to what? It tells the processor to do something?
Yeah, let me repeat again, okay?
And then it goes to the
let me repeat again, okay? Let me repeat again, okay? So basically in your memory, right? In your memory, you have 3 sections, right? Let me write again. This side is the main memory. Main memory, you have 3 sections. You have stack segment, you have data segment, and you have instruction segment, right? So in instruction segment, it just stores something like this, like binary code. And the binary code actually means the right-hand side assembly. Is that okay? So your program basically, when you start, actually storing here, right? And then my address is like 4000, right? So here in my CPU, I have something called program counter. So my program counter has this address. So I go to here, get my first instruction. So I get this one called like AFA4000. This is my instruction. And this instruction means load some register with some value 0 or something. Okay. So this is the machine code. This is the assembly code. And that means loaded back to my instruction buffer. So I know that this is the next instruction I'm going to run. So my program under this instruction actually sent to my control unit.
What does the control unit do?
Control unit actually say, okay, you have a load, right? So let me actually load the data so I send my control read to my 3 bus, and then get the data from my data segment, and then load that data from my data segment, load the data from my data segment to some register I have in here. So that's what the instruction actually finish. That instruction only have the load function. Okay, so you prepare the data. So basically, it just comes from memory and load to the register. And what's that for? I don't know. That's the instruction 2. Maybe you load one, the next instruction you load another one, and then after that you register 1 plus register 2 send to register 3, right? So you may need 3 or 4 instructions to complete one action, like A plus B in high-level language equals C. You may need 4 or 5 instructions to finish it. The first one, load A from certain memory location. The second one, load B from certain location to the register, right? The third one, you actually need to add register 1 with register 2 and save to register 3. And then the next one, you write your data from your register back to my data segment. But in order to do that, each of the instruction, the 4 instructions, actually save in this one instruction segment, and one by one it can load to the instruction buffer. One by one it can load to the instruction buffer, and then the personal program counter will come and get the program. So this one actually is only data path, is not complete. Let's look at some other slides. It may show you better. I mean, this one is no good. Let me show you. It should be in chapter 4. Okay. Let me show you in chapter 4. So this, whatever we talk about in computer system organization, maybe in the long run, you become a programmer. maybe that's not important for you to do some program like this, but it's good for you to understand what's going on. Okay, so for this one, you divide hardware, you have control, right? And you need to do some algorithm like that. Let me see. Okay, the processor. Let me show you the process. The CPU. Let me see. Okay, this one is a better chart than the data path. So whatever you see on this one and this and the other one, let me close this. This is not going to be useful today. And this one is only data path. Okay, the right hand side is the real whole CPU chart. The right hand side is the whole CPU chart. Okay, left hand side. Actually, let me bring this one to this side, and let me actually bring this one to this side. Let me minimize it. Okay. Can I just don't have this one? Can I just minimize this one? Yeah, and then move this to here. Okay. Can I just close this one? Okay. So right hand, this guy actually is a data path, right? So this data path on the left hand side. On the left hand side, it just represents this guy called register is over here. This guy called ALU is over here, and there's a data memory. Okay, data memory is some cache or something. So this one actually can be outside, can be on your board memory location. Okay. Okay. So whatever we talk about here actually is like just like what I drew. It's like data segment and maybe instruction segment. Okay. Maybe like that. Okay. So that's clear this. Okay. So every time actually from this chart, you actually get some instruction from here. So your program actually been listed over. You have several programs, just like Hello World, you have every program. So every time the instruction got loaded to instruction memory, right? So and each time actually usually is loaded like 500 block of code being put here, right? And then your program counter take a look on the instruction. Okay, that the instruction I'm not going to run. So actually, this one control unit it send out the control code to the register, to the ALU, to everything to control it to run. So that's the instruction buffer, and also you have the your CPU to run it, to do your data path to execute the program. Okay, so data path is only one part of the US processor. Okay, so basically you need to understand that you had a control unit, you had a memory. So memory, you have memory write, memory read. There's a control. You load your control signal. You load your program. You load your program to the instruction buffer. Put program counter pick one and send to control unit. Control unit send to control what I should do or whatever I should do over there to control the whole data. Like load data from memory to my register, load data to my memory to my register, and then add together and write back to my memory. Okay, those guys are controlled by control unit, but control unit listen to the instruction stored in memory. So each time you load an instruction to here, send to control unit to decode it, and then load another one, send to controller to decode it, load another one, send another one to decode it. Okay. So there is something called cycle. That's called instruction cycle. Okay. Later I'm going to cover this. Okay. Right now, let's just leave it like that. Something called instruction cycle. So each instruction you load from your memory to your CPU and you run it. It's called instruction cycle. It's called instruction cycle. So instruction cycle is like fetch instruction, decode, execute. Fetch instruction, decode, execute. Get instruction from memory, decode it, and then execute. Get instruction cycle. You know what I say? This is the instruction cycle. Is that okay? This is so-called instruction cycle, very basic instruction cycle. Okay, so for every CPU is something like that. Okay, there is an instruction cycle, and there is another one called machine cycle. Machine cycle has fetching instruction, and then decode is queue, and then you need to add store. So real computer is running this machine cycle, not the instruction cycle. The instruction cycle from the programmer point of view, it's just fetch, decode, execute, fetch, decode. But actually, they have a 4 cycle, even 5 cycles, depend on your processor. So the processor right now, actually, we call it a microprocessor. It actually is more robust than this. So we would have the so-called RISC instruction pipelining. Okay, so RISC instruction pipelining is like, this is the so-called pipelining. So the real computer usually is something like this, okay, not like that. You have the instruction fetch. So I get my instruction, this one is instruction, get the instruction, this one decode, and then it's queued, right? After it's queued, I actually access my memory, okay? And then write back my data to the memory. So actually, like this one's a 5-stage instruction. But you cannot wait for 5 clock cycles, so actually, we can do the second instruction, just follow it, then just follow it, then just follow it. This thing is called pipelining. So on each cycle, I almost run 1 instruction. Instead of, in the old day, we have 1 instruction finished, then run the second instruction, then run the 6th instruction. This type of process is called CISC processor. This type of pipelining is called RISC processor. Okay, they are different style of processor. So here we have the RISC compared to CISC. Okay, we have the RISC compared to CISC. Okay, so there is a certain type of instruction cycles. Okay, so that's the instruction cycle. But we right here we don't want to branch so far for those topics. So basically, your ALU need to work with your ALU need to work with your control unit. Your ALU need to work with your control unit. That's one thing. Second, your control unit actually your instruction every time you actually has instruction fetch, instruction decode, instruction execution, and then memory access, and then write back your data to memory. That's a whole instruction cycle. Each instruction goes through the 5 cycle, and then you do instruction by instruction. You do instruction by instruction, just like your QT spin here. You can do this stepping. You do one by one, one by one, one by one, one by one, one by one. And the reason why I say it's a score keeping is like after you do one by one, my register keep changing, my memory keep changing. Those are so-called the scoreboard right here. If you don't look at the register, the memory is in this data section. So assembly programming is like just like you write something, you load into this QT spin, and then you go through it one by one, check whether the data is correct or not, whether you print out to your console or not. So similar to C programming, but a little bit more tedious. Okay. And this one really is the whole processor chart. So right here, let me actually just copy this guy and pass to your Facebook, so you can see it right away. This chart is more important. Then you have the whole view of what is a processor instead of just as a data pass. So that's why I say your Tenable book is a little bit too easy. So there's a few things. Number one, your program counter is in charge of everything. So actually, program counter is actually a pointer. Program counter is a pointer, point to your current program, right? And then your current program got loaded into the so-called instruction buffer. An instruction buffer was sent to some register you call instruction register, and instruction register will be decoded by decoder. So every time you get an instruction from memory, put into the buffer in the instruction buffer, and instruction buffer, CPU program counter pick the current one to the instruction buffer, instruction register, and that got decode. Decode after that you execute the ALU operation and write back. Okay, so that's the whole process of what has been done here. So basically you have the program counter, you have instruction register, and then you have those guys who execute the data is called data path. Data path including register, ALU, and the memory I/O unit to access the I/O part. Okay, so here we actually try to give you some basic concept of CPU, and then the instruction have two types. Instruction can be have two types. One is called register memory. One is called register to register. Register to register means like add integer 3-way add. Okay, I add my R1, R2 assigned to R3. Okay, and then I may have a add integer, add the memory integer 3. I have a R1 add R2 assigned to R3. That's some memory. I'm sorry, some memory MEM or something, some memory. Okay, and then I may have the add MM3 like R1, M1, M2, something like that. So there are several types of memory access model, but primarily you need to remember register memory instruction and register instruction. Register memory instruction allow memory word to be fetched into registers where, for example, they can be used for ALU input in a subsequent instruction. A word might be an integer. We will discuss the memory organization later. So memory model is the key. Whenever you do C programming, assembly programming, you need to be aware of what is the memory model you have, okay? And the other kind of the instructions is register to register. So which one is faster? Register to register and register to memory. Which one is faster?
Register to register?
Yeah, of course, it's on chip, right? Memory, you need to go outside, okay? And then the process of running two operands through ALU and store back is called data path cycle. So data path cycle is actually, what is data path cycle? Data path cycle is like from register 1 to register 2 to ALU, and then to some to write back unit. This part is called data path cycle. Instruction cycle means instruction cycle, instruction fetch, instruction decode, instruction execution, right? Two combined together called machine cycle. Instruction fetch, instruction decode, instruction execute, right? Write back. And memory access, I'm sorry, MEM, memory access. And then after that, write back. Okay? So machine cycle is actually more complete. So you just need to, some people also call machine cycle as an instruction cycle. So here we have this one called instruction execution. The CPU executes each instruction in a series of small steps. Roughly speaking, the steps are the following. Fetch the next instruction from memory to the instruction register. Change the program counter to the point to the following instruction. So program counter always pointing to the next instruction. So it's somewhat like a pointer. I get my instruction, run it, and then I advance to the next one. So this program counter usually only one operation is done, increase. But if you have the if then else, then it may be jump to some other edges. So PC may be updated by something. Okay. So that's the jump. Or you have a function call. And then if the instruction use a memory, then you need to determine where they are. That's called memory cycle. So after execution, instruction execution, there is a memory cycle because you need to go to the memory, get the data, come back. Or you address, send out the address and then write back. So usually the memory access take 2 cycles or more. 2 cycles or more. Memory access 2 cycle more. It's actually slower than register. Okay, so you can get the data back to the CPU and then execute the instruction. Okay, so the fetch, decode, execute cycle. These screens often refer to the fetch decode cycle, and it is also called as the instruction cycle. It's central to the operation to all computer. And in terms of detail about the cycle, every instruction may have different format. They could have more than one format of the instruction cycle. The description of how a CPU works closely resemble a program written in English. Okay, so it's just like something just similar to a program. And figure 2.3 inform program rewritten in Java called interrupt. Let me actually see the next one. Figure 2.3. So this is instruction step. The next one is interpreter. Interpreter number 1 is rewritten in Java. So basically, you have some sort of interpreter and your program counter, accumulator, instruction type, data location. So basically, it's trying to mimic the function. So you can see it as a pseudocode for your processor. So basically, you assign your starting address to your PC, and while you have the run bit on, so you keep running the program, you get from PC's memory locations PC to get an instruction, and then you advance your program counter. Next time you will actually get the next one. So basically, you can do that. You can actually think about the program counter is like this. If you don't have this one, you can actually put here like PC plus plus. So you get your current PC program counters data and use that as the instruction. And because the program counter is a pointer, so you actually this is equivalent to instruction. This is equivalent to instruction equals PC plus plus body. I'm sorry, I showed it wrong. Okay, it is equivalent to PC plus plus body. Right, you get a body first, and then you advance your PC, or you probably this one's better. Get the body of the PC and then PC increase, because actually you get the memory content is actually PC pointing to some instruction. You get the instruction back to my instruction, and then I advance my program counter. Next time you will go to the next instruction. So actually you get the instruction and then determine the instruction type. So instruction type, it will be the register memory or register register, right? And then you try to find data if you have memory to memory location. So basically you use the pointer data location to find the data and then execute the instruction type and the data. So that actually means if this one is like register to register, and this one all register to memory, right back to memory. So you need to get the memory and get the data, and then you actually do add, and with that different data loaded to your CPU. Is that okay?
Mm-hmm.
So basically, this one is a pseudocode in Java language. Try to explain how the instruction got decoded. Okay. So here we have that 2.3. We have that, and then whatever this one's because it's pseudocode. It just give you some idea of what it is. And then you go back to talk about 1950 something, those garbage. Okay, you talk about those garbage in 1950 something. And the next one for this one. So design principle of the modern computers, all instructions directly executed by hardware. Maximize the rate the instructions are issued. So that's why we may have the pipelining to make the program faster. So that maximize the rate. We want the instruction directly executed by hardware. Try not to have several level of the interpretation. And instruction need to be easy to decode. So don't try to invent some instruction that is hard to decode. And then only load store to reference memory. So actually, people give up. Usually the modern computer don't prefer this one. Don't prefer this add register 1 with memory 1 and then memory 2. This one usually doesn't work, because this one may take a lot of cycle, a lot of time to go up chip to get memory. So right now, usually it's like load R1 with memory 1, load R2 with memory 2, and then I add R1, R2 to R3, and then I store my R3 to my memory 3. Okay, so modern day they like to have this low store architecture instead of putting the memory register to memory type of instruction. So that's the trend. Okay, it doesn't mean that every computer is like this, but that's the trend. People like to use the low store architecture. So if you look at the processor, if you look at the processor, you can even use the word called low store architecture.
What's it called? Lost? Load store.
Yeah. Try to minimize the, you see, it even has this terminology called low store architecture. So try to minimize your memory access inside the instruction. So you load something, add something, and then store to something. This is called low store architecture. Is that okay?
Mm-hmm.
So here, let me save to something, and this is good article anyway. Okay, that's why before we really talk about the MIPS processor assembly language, we have to know about this kind of the computer architecture. Otherwise, you can do it. And then because of the low store architecture, we need to provide plenty of registers. Why? Why we need to provide plenty of registers? Because you are doing a lot of loading, right? You load something to register 1, register 2. So they meet those registers as a buffer. Otherwise, if you run out of register, what should you do? You actually need to purge some of them, load something, reuse some register. And later, if you miss it, you have to go back to actually read again. So the bigger the scoreboard, the bigger your register is, the compiler can actually be more efficient and then run the code in more efficiency. So basically, it's a so-called instruction level parallelism to be explored. We try to do something called pipelining. So you actually break down your instruction into 5 cycles. Instructions fetch unit, instruction decode unit, and then operand fetch unit. You get the data. Okay, this is memory cycle, and then instruction execute unit, and then right back. So right here, you may see it actually is different from what I say. Some people have this instruction fetch, instruction decode, and then this fetch operand, and then execute, and then write back. Okay, and it may also be instruction fetch, instruction decode, execute, memory access, and then write back. Okay, which one it is? that depends on your processor. And what is the definition for memory access or fetch operate? It all depends. It all depends. And some people may use a four-stage pipeline. Some people may use a five-stage pipeline. Some people may like to use six-stage pipeline.
Okay, so
It
it's
all
like
it all
personal.
depends. No, it all depends. Just like different people write different program. And who decided? The CPU designer will decide it. Okay,
Okay.
CPU designer will pick each architecture. It has its own levels. Okay, so that's that. This VEC stuff, I would just like RISC and CISC. I talk about it. RISC is like I simplify my instruction set and try minimize register to register memory execution. And CISC machine is like six is complicated. Okay, so complicated instruction set. You have instruction one, finish, and then do instruction two, and then you do instruction three. RISC is like I try to simplify my instruction so I can pile up everything like that. So who is faster? CISC or RISC? Which one is faster?
Um, CISC?
No, RISC is faster.
Why?
This over the time you use this is maybe five cycle.
Oh,
You do 15 cycle to finish three instruction. Right here, how many? Say if it's five stage, then how many? Five plus two is just seven cycle. You finish the whole operation. Okay, so that's what people say the parallelism. That's called a parallelism. Instruction level parallelism. You try to explore the instruction level parallelism. That's make the execution faster. What is the instruction level parallelism? Say right here, my first instruction is like this, right? I first operate. The second one may be running like this, right? But this one right back, say I have like add R1, R2, and then right to R3, right? But if my second one is add again, but like my R3, R4, R5. So this R3 needed for R4. So actually this is fifth stage cannot catch the third stage in the next instruction. Then there is a dependency. There is a data dependency. So the pipeline will block. It called pipeline store. They will call the pipeline stores. And because of try to minimize the pipeline stores, so we need to rearrange the instruction, say insert some instruction that is not used in front of it, doing reorganization, and that will make your CPU faster. So right here we are not doing that. We actually using the CPU. We are not doing that. But you have to know that the higher level of the parallelism, reducing the data dependency, control dependency for the instruction will optimize your performance of your CPU. Is that okay?
Mm-hmm.
So that actually, so there is a whole theory about how to make program faster. Okay, there is a whole theory of how to make your CPU faster, and it's not what we are talking about here. Okay, we just briefly talk about it right now. So the next one, the design principle of the modern computer. In the textbook, it has the detailed explanation of what it is. But here, I just give you some idea. Okay, so usually try to use the low store architecture instead of doing two machine. And then there is an instruction level of the parallel that need to be explored. Okay, but there are several type of process being invented. Okay, pipelining is only one of them. Pipelining is only one of the parallelism mechanism. There are some other one. So the data path design actually has the basic part, okay, basic. This one is called pipelining. This one is called super pipelining. This one is called VLIW. This one is super pipelining with parallel, super scalar, super pipelining. Here's instruction reorder. So the data path is like there are some people who do computer architecture and always optimizing the instruction set, optimizing the data path. So this is one of the important job for computer engineering. There are some people spend their whole life to do something like that, and then nowadays there is not only one ALU, two ALU. There's two floating point unit, and there are two low store unit. So here you will see that there's a low unit, there's a store unit, two ALU unit, two floating point unit, and then the instruction come in. Actually, there's a branch predictor. You know why? Because you have some event else. I may predict how much percentage I'll go yes, how much percentage I'll go no, something like that. And you fetch your instruction set from your CPU, right? Put into 32K instruction cache, and then fetch the queue, and then decode. And then decode, you run some micro program, and those micro programs help you to control US data path. Okay, so the CPU right now is very complicated. You know, the chart we show you is like very basic one. So the nowadays have the reservation. This is a whole course that if you study the 152 ICS 152 computer architecture, the one I say that is like the one after the system programming. This whole course talking about this. There's a whole course talking about this. So you actually starting to have some data paths. Left hand side is the CISC. Whatever we see right now is CISC. Okay? Whatever we talk about right now, the chart is CISC. It can be chopped down into 5 stages and it becomes RISC. Right hand side is RISC. Left hand side is CISC. So whatever I told you, the MIPS, whatever inside those chart, that's actually a chart for CISC. A MIPS, a RISC processor will look like this. Okay, and then there is a superscalar. The superscalar and pipelining is different. Pipelining is like I actually chop down 5 stages, right?
Yes.
I pile up like this. Superscalar is like, why don't we do this? Why don't we do 2 instructions in one cycle? Say I have this one called load memory 1 to R, right? Or load my memory 2 to R, right?
Mm-hmm.
And then actually it's just like my load my A to R, load my B to R2, load my A to R1 and load my B to R2. And these two actually parallel, right? No dependency. Those no dependency one actually can put 2 instruction fetch and then 2 decode, 2 execution in at one time. This one is called superscalar. Superscalar. So there is a one called.
They do more things at one time.
Yes. As you can see, almost double the throughput.
So why would I ever use the pipelining?
This is still pipelining.
Oh, this is still pipelining?
It's just like two instructions.
So why would I use scalar?
Why do you use scalar? Sometimes it break. This one is because I assign A to R1, B to R2, right? But if my A to R1 followed by R1 to B, then what will happen? And then load B to R2. So this B to R2 cannot be actually directly being used. You know what I'm saying? Mm-hmm. So there's some dependency will happen. There are some dependency will happen. There are certain so-called dependency. There's a flow dependency.
Okay.
My data, I finish the assignment and then the A will be used by the other one. This one is called my flow dependency. There is an anti-dependency. Anti-dependency means like this one I get the data, right? This one I get the data and then it actually been used over there. And this one, it actually assign this data. But if this data cannot go over ahead of the S1, otherwise the data will be written to here and it will cause problem. So this one is prevented for the out of order execution. So this actually you need to actually study the data dependency. There's a special study for that. If you cannot fill the pipeline, you will create some bubble or extension of the time is needed. And that's a waste of your CPU. You know what I'm saying?
Uh-huh.
So that's what being studied, but that's not what you need to worry about right now. It's actually in 52 cores, 152 cores. So there's a prefetch buffer, there's a pipelining, there's a stage, something like that, okay? So this actually we cover this. And there's a superscalar architecture. So superscalar architecture is like, okay, I provide you double the resource, 2 instruction, 2 ALU, or 3 ALU, or 4 ALU, or maybe 2 floating point processor, and you do more job at the one cycle for me. Okay, but again, you may not be able to fill it 100%. Okay, you may not be able to do it 100%. That's called pipelining, superscalar. Okay. So here, actually, I just briefly talk about this. The next one, this one is the processor with superscalar. Say this one had 2 ALU, 1 load unit, 1 store unit, and 1 floating point unit. So usually, in a CPU nowadays, CPU usually like 2 ALU or maybe 4 ALU, and floating point usually 2 floating point unit. And load store sometimes they have a share one, sometimes they have load store. Sometimes they have share one, sometimes they have 2 load, and maybe 1 store, or 2 store, 1 load, or something actually for CPU design. You know, you want to have more function, but you cannot afford to put too many because of your complexity of the CPU design and efficiency and the resource management. Then we need to explore the processor level parallelism. Okay. And then here has something called SIMD, MIND, and SIM, whatever. There are several names. There's a single instruction, multiple data stream, CPU. That means that I have a CPU. I only have 1 instruction coming in, but I may write 2 data out because these 2 data actually take more time, right? Data actually take more time. And there's MIND. That means I can fetch multiple instructions at the same time. That's
so it's just like having more like processors and stuff, right?
Yeah. Whatever I/O or whatever resource or whatever you actually give you more resources.
Technically, it's still the same process, but it's just having more processes.
Say from the guy who do C programming, he doesn't know. He doesn't know the compiler GCC, how will it compile to. And remember that you have some so-called pragma, and then parallel, right? Say you have a C programming pragma that will compile to multiprocessor format. Your execution code will be compiled to your C program may be compiled to multiple processor format. So for C++ language, they have this pragma stuff, OpenML pragma. and you will compile to SIMD, right? SIMD, right? You see here, single instruction, multiple data stream, right? So there are something that you can do to help you to achieve this, okay? And they need to have a special compiler to achieve that. And something called vector processing is also possible. It actually usually is like, if your CPU is like load R1 to R2, right? Load R2 to R3, whatever. That actually spend a lot of time, right? But the better thing is like, if possible, I actually do vector processing. My vector V1, V2, V3, V4 time with my processor V1, V2, V3 or something. It's just like when you have matrix operation, right? This line I put it here, this line I put it here, and then two multiply at the same time and getting the result. It's called vector processor. It's way faster in hardware design. It will be way faster to have you rely on the instruction. You know what I'm saying? Mm-hmm. And then after that, we have this multiple core. Means we have 4 CPU on one board with a single memory. So right now, the newer i7 has quad core or even 6 core, right? That's called multiprocessor. That may make a computer even faster. That's called multiprocessor. That's in a single computer, you have multiple processor. And the next one is called multi-computer. Multi-computer is not multiprocessor. Multi-computer means like I have 3 computers put it into one mainframe cabinet. And that's 3 computers, each one doing its own job, but they can share resource. That's called multi-computer. Is that okay? Mm-hmm. That's different from the multiprocessor. Okay, so CPU in the multi-computer are said to be loosely coupled because they each other run independently. And those one in multiprocessor, they are tightly coupled because each one may depend on the other one, okay? The next one, primary memory, you have bits. You have, let's look at the slides. The superscalar, we finish it. Processor level parallelism, we talk about it. Processor parallelism, we talk about it. Okay, memory. When we do memory, we have 8-bit as a byte, right? And in each address, we have 1 memory byte location. So let's look at the single bit, okay? A single bit in the CPU can be as small as, the single bit in CPU can be as small as a capacitor. Okay, it can be as small as capacitor. So I store my charge over here, it becomes high voltage, and it's 1. I discharge it, and it becomes 0. So the memory, so-called DRAM in your memory, can be a capacitor. And capacitor in the semiconductor, you may have the so-called deep trench. Deep trench DRAM cell. Okay, what is DRAM deep trench cell? Okay, so right here, this one is called a memory bit. A memory bit is like this. Okay, what this is? Let me show you. Okay, let me show you what this is. So this guy actually, I mean, wait, where is the deep trench memory now? Okay, this is the deep trench memory, right? So what this guy actually logically is like, there is a so-called bit line. Okay, this is a so-called bit line. This bit line is the address, right? It's an address. So there's a line like this, and it control a transistor, right? It control a transistor. And there's a data bus. There's a data bus. Let's use different color. This data bus single point connected to this one is bit line, and this one's the edges is select bar. Okay, and you have a capacitor over here. Okay, so what it is, like I use a driver over here. If I want to write a 1 over there, I will actually write a 1 charge to here. Okay. If I want to read data out, I actually read the data from here to with the amplifier to read it out. So basically, I just need to charge discharge over here. It finish the so-called memory operation. So each bit is like this. Each bit is like this. Okay. And the bytes actually have A of them tied together. A of the capacitor byte tied together. So your memory organization will be the chart on the textbook is not good. Okay. So that's the deep trenching has different type of trenching to improve the maximum charge that can be stored on the DRAM. So here let's say DRAM organization. So your real DRAM will be organized like this. Okay, the memory you actually use will be like this. Okay, so basically you have a many column and row. Each one may be 1 byte or something. So your address bus send the address over here, decode, right? Decoder, and then pick a certain row, and then some part of the address is sent to row column buffer and decode some column, and then you pick this one, right? And then there is a control command that actually is a control bus decided to read or write. Okay, so for example, this one is read, then the data will be shipped out to the row buffer and then read out over there, right? And then it actually sent to the data bus to get out from the memory bank. Is that okay? Mm-hmm. So that's how your memory DRAM is working. Okay, that's how your DRAM will be working. That's how your DRAM will be working. So basically, your DRAM can have a lot of control logic in order to make it work. Okay, you have read, write, enable, write, enable, read, enable. Okay, here you have try to get the address bus, decode the address for row decoder and column decoder, pick the cell, read out the data. So that has complicated organization, but it's not a topic right now. The only thing you need to know is that there are 3 buses. You actually have the address bus that send out the address to enable a bit to be read or write. There's a read-write controller on the control bus to decide to write data into the cell or read out from the cell. There is a data bus that will send data in or ship data out. Okay. Okay, so that's this. I think per cell. This one, okay. The next one is the byte ordering, called big ending and little ending. Okay, all the Intel processor is using the little ending. Okay, it's using little ending. What is little ending and what is big ending? This is Motorola. Motorola uses this one. Okay, for example, I have an integer, right? Say my memory location starting from 4000, 4001, 4002, 4003, right? Mm-hmm. For example, I have this, right? So basically, this is each one has a bit 1 byte, right? For example, I want to store this one 0, 1, 2, 3 in there, right? I want to store real 1, 2, 3. This is a hexadecimal value. Hexadecimal value. I want to store this in, right? Little endian is little endian. So my low address is stored with this one 3. Let's call little endian. So the most significant data is stored on the higher edges. So higher edges, say this one higher edges. I'm sorry. I messed up a little bit. Yeah, I'm sorry. Last soon like last soon like last soon the 3 is of lower edges. Okay. So the highest edges. So the edges is like 0. I'm sorry. Is 0, 1, 2, 3, right? So this is 4003. This is 4000. So your 3 store this. And this is most significant byte is 0. So this one is called little endian. And then big endian will be stored 3210. Is that okay?
Mm-hmm.
So just look at the name. It ends with little. It ends with little data. Okay, so the first one is off. So say right here, say what's this actually? Jim Smith, right? Jim Smith. So Jim Smith, your data is like Jim Smith. So Jim is like higher order. So I put my Jim over here. So Jim Smith, something like that. Right? That's called little endian. So each time I put 4 data in there, it's read like this. We call little endian. Is that okay?
Mm-hmm.
I think this little endian chart, this is textbook's little endian explanation is no good. Okay, let's look at something else. The chart is confusing itself. The chart is confusing itself. Let's look at some comparison. So this one, your data say, your data is, this one is your data, right? Your data is like CAFEBABE, right? This one the lowest significant bit. So this is bit 0 to bit 31, right? You have 32 bit, right? So your BE being stored right here at the first memory location. At the first memory location. That's called the byte 0. That's called little endian. And then byte 1, byte 2, byte 3. Is that okay? That's called little endian.
Mm-hmm.
That's the way 4 bit have been shipped out. So let's look at another example right here. Okay. So you have this one, little endian memory. So this one, the smallest number stored at the higher edges. That's called little endian.
Mm-hmm.
Now this is still confusing, this one. You try to store your data D7C4, right? So C4 is least significant. You put at the memory location 0. That's called little endian. Is that okay?
Mm-hmm.
And memory byte 1, you store DC. But in fact, if you think about it, D7 actually is higher value, right? Higher value stored at higher edges. That's called little endian. Is that okay?
Mm-hmm.
It looks like somewhat like it's crossover, but in fact, that actually is confusing. You just think about your higher byte stored at the higher edges byte. My lower value stored in here. Why it actually called little endian is because like it looks like it's crossover because your data is something like this, right? D7C4, right? If you fetch my whole 16 bit, it actually should be like bit 0 to bit 16. and then I don't load my data D7 C4 out. No, you actually first byte actually is C4. So that's called little endian. Okay, so that's the way the little endian being stored. So this part is somewhat not easy to understand. Okay, and the IBM has a BCD binary coded decimal, but it's no longer used. Okay, nowadays people use ASCII code and Unicode. And memory address is like location. You can use that to access your memory. And in terms of how many bits to calculate, here has some detail. By ordering, we have two types of by ordering, big endian and little endian. Big endian is Motorola way, little endian is Intel way, and nowadays it's all little endian. So the idea is like, if I have data called 0123, it will be stored lower address with 3 and then higher address with 0. Okay, so that's called little endian. But the chart actually confusing right here. The chart actually confusing that right. For example, you have first byte, first integer is 0, 1, 2, 3, right? It actually starting from stretch 0. So here this is actually address 0, 1, 2, 3, right? And 4, 5, 6, 7. Right? This is what it is. But the data it read out as an integer will be 0, 1, 2, 3, 4, 5, 6, 7. This is big endian. Little endian is different. I store my least significant byte at my first location, and the data should be read out this way, 0, 1, 2, 3. Should be read in that way to get the right value you would get. That's called little endian. An error correcting code. Error correcting code is actually something that can detect the number of bits. And this one actually I should have a separate after we talk about the bit level operation using digital logic. I'll talk about this error correction code right now. This one's putting in here is not appropriate. So that's a primary memory. Let me see. The size of word. You can read the book, okay? That is not important. The next one is correct bit, parity bit. This is actually too much. Cache memory. Cache memory and the CPU memory is, cache is on chip. Memory is off chip. And memory usually is using the DRAM style. DRAM style, as I say, it has the deep trench. It has a deep trench capacitor. So the one that we use to build the CPU is called logic process, and then it's different from the DRAM process. When you do the chip building, it actually has different process. One is called DRAM process. The other one is called the logic process, and the two actually are of different process. Okay, so here actually we want to build some memory on chip, and those memory on chip is called cache memory, and cache memory provide some sort of buffer. So basically, your CPU may have some cache. So what it is like, usually when I get the data, if I go all the way to memory, it takes longer time. But I can actually get something, put it in here. Since I know where is the data segment, I can prefetch something over here. So my CPU, instead of going to memory, I always actually update with here. Only when you have some update on the cache, you have two options. You can write back to here or write through. Write back and write through are different. The write through scheme is like I just directly write to memory. So cache got updated, and then memory also got updated, but it's inefficient. That actually dilute the purpose of having the cache. Having the cache is that I happily do this only when the same memory address need to be read from other people. You write back at that time. Say here, I have a lot of writing. Say my memory 1 equals A, and memory 2 equals A, and memory 3 equals B. 1, 1, 1, 0, 1. Memory 1 equals X. Memory 1 equal T, right? Only when one day I use memory 1 need to be read by X. At that time, I write my data from my cache to memory. You know why? Because I need to keep the memory and my cache consistent. Other than that, every time I update my memory, I can update to my cache. So cache got update. The M1 on cache had a fresh copy until it is used by other people, and then I need to write back to my memory, make sure the copy in memory is actually healthy. So that actually there are some memory management issue, and there's a locality issue. Locality means like in CISC design principle, it said that 90% of the memory only get 10% CPU time, and 10% of the memory get 90% run of the CPU. That's why we load allows about 10% of my data from memory to cache. It's good enough to support 90% of the computation in the CPU. Is that okay?
Mm-hmm.
That's why we want to have a bus. And if it means, then if I don't get the data I need it from cache, then I just fetch it from memory. And that penalty is lower because only like 10% I need to go to my memory to get some data. Okay? Memory packaging and style. You have this kind of DIMM memory. I show you this already. You have something called this SODIMM memory. So your memory hierarchy is like register write to cache, cache write to memory, memory as you write to solid state like SSD flash memory, and after that you write to tape or the hard disk or optical drive, DVD or something. And the magnetic drive is out of date now. This one I'll just bypass. It's not important. You read your own book, okay? It's a waste of time. So I actually, I'm not going to cover this at the time. Okay, this one disk or whatever, and this IDE disk actually you just read it. Okay, it's not an important issue, but there are some terminology you need to know. Okay, it's not a purpose for doing this computer organization. So great, you need to read it. Okay, you need to read it recently, but. Okay, the next thing is this control gate and semiconductor for flash memory. Let me see. Here talk about a lot of I/O, but okay. I think today we are up to here.
Okay.
Okay, and then next time.
So I still have to do the homework from last time, right? Chapter 1, mode 4 equals 2 questions.
Yeah. And then also read this chapter 2. You know, let me know when you read chapter 2 what you don't know. But this part is not a core for the assembly. You know, the computer architecture. So next time I will start from chapter 3, the logic design. Okay, logic 2, chapter 2 actually is just reporting a lot of historical issues like what is hard disk, what is drive. Okay, today I'm more focused on the CPU structure. I don't want to spend that much time on those hard disk or something. It's actually related to computer architecture, but it's not so related. You know, this hard disk, bubble memory, these things actually are just normal traditional computer knowledge, but it actually is not related to CPU. So you just read for yourself, okay? And then for the homework, you can just do what we talk about, still do the mode 2 problems, okay? Or chapter 2 as well, okay? Thank you. Bye now.